Howdy, howdy. This is Mr. Potter. In these last chapters, we're going to be taking the calculus that we've learned and we're going to be applying them to some real world situations. And so in today's lesson, we're going to be talking about using our calculus with parametric expressions. So I actually want to start today's lesson with a little bit of a recap of what we're talking about when we're dealing with parametric expressions. Normally, we think of y being some function of x. In other words, my y is really a function y of x, where x is my independent variable, y is my dependent variable. But when we're dealing with parametrics, we're actually dealing where x and y are both functions of a third variable t. And so instead of dealing with our parametric function as really being kind of x comma f of x, or x comma y of x, what I'm actually dealing with parametric functions is I'm dealing with some x of t comma y of t. And so the way that I determine my points is by plotting each of these functions for different values of t. And so this brings up some interesting stuff. One of the ones that we see a lot in pre-cal is where we let x be cosine of t and y being sine of t on some domain, say from 0 to 2 pi. And so when I do this, if I graph this on my coordinate system, if t is 0, then cosine of 0 is 1, and sine of 0 is 0, so that's actually going to be this point. And as t increases, the cosine is going to be decreasing, but the sine is going to be increasing up to a point where at t equals pi over 2, cosine of pi over 2 is 0, sine of pi over 2 is 1. And now as t increases, cosine becomes negative from pi over 2 to pi, but sine is decreasing towards 0. So I end up with this shape here. And as t continues to increase, I end up tracing what amounts to a circle with a radius of 1. Notice that my endpoints are at t equals 0, which is this point here, and at t equals 2 pi, which is this point here, but they both happen to coincide with the same point on the xy plane, that is 0, 0. Another way I could look at this is if I was to take a function where x of t is square root of t and y of t ends up being t minus 2. So now if I take a look at this on some domain from 0 to 4. If I start substituting in my points when t is 0, the square root of 0 is 0, and 0 minus 2 is negative 2. So I actually end up with this point here. At t equals 1, the square root of 1 is 1. 1 minus 2 is negative 1, so I get this point. At t equals 2, radical 2 is 1.414. 2 minus 2 is 0, which means I'm hitting the square root of 2 right here. I'm hitting the square root of 3 at 1, and I'm hitting the square root of 4 at 2. So I end up with something that actually looks like the right hand of a parabola. But because I'm stopping short here, I actually end up with just a that was uncalled for. I actually end up with something that just kind of stops short. And so this part actually isn't part of my graph. So I can do a lot of descriptive stuff when I'm dealing with parametric equations, or when I'm dealing with parametric functions. I can even talk about a graph whose graph itself is a relation, even though x of t and y of t are both functions. So in other words, I end up with a curve that doesn't pass the vertical line test, even though each one of the functions x of t and y t are functions in and of themselves. Of course, this is a calculus class, so we're going to be looking at this in the context of calculus, and so I want to talk about our friend the chain rule. Now, since we're talking about x really being some function of t and y being some function of t, when I talk about x prime, I'm really talking about the derivative of x with respect to t. And when I'm talking about y prime, I'm really talking about the derivative of y with respect to t. Keep in mind that this is not slope, because slope is a completely different quantity entirely. Slope is the change in y over the change in x. Now, of course, if we're looking for the slope of the tangent line, I'm actually looking for the instantaneous rate of change. So I'm looking for dy dx. But this kind of assumes that y is really a function of x. We have y as a function of t. So if I want to take the derivative of something involving y, that would be dy dt. And now I've got this dt that I really don't want, and one of the things I can do is get rid of it. And I can do that by multiplying by dt dx, but keep in mind that this is really the reciprocal of x prime. So what I actually end up with is that my slope is really the change in y with respect to t divided by the change in x with respect to t, because dividing by a fraction is really the same as multiplying by the reciprocal. So I can talk about the slope of my graph by looking at this relationship between y prime of t and x prime of t. If I want to talk about the concavity is really looking at the change in respect to y with respect to x squared. In other words, the second derivative. Now, what this really meant for us back in chapter 4 is we were looking at the derivative of y prime. But this was really y prime of x. So what we're really doing is we're looking at the derivative with respect to x of this dy dx that we had. So in other words, this is really going to be the derivative of my slope with respect to t divided by the derivative of x with respect to t. So finding this concavity, finding the second derivative of y with respect to x is a little bit more difficult if I don't in fact have y as a function of x, if I have instead y as a function of t and x as a function of t. And I do want to go back to the first example we were talking about, the example where I'm dealing with y being the sine of t and x being the cosine of t. And when I look at this situation, if I want to find the slope of the tangent line, I need to know what the derivative of y is, which is cosine of t, over the derivative of x, which would be negative sine t, and this gives me negative cotangent of t. So in other words, the slope at any point on my unit circle is going to be determined by the function negative cotangent of t. So looking at this, if I'm looking at my unit circle and I want to talk about what's happening at t equals 0, t equals 0 gives me a cotangent that's undefined, and so my slope has undefined. That gives me a vertical line for my tangent line. If I'm looking at pi over 4, pi over 4 is right here, and the cotangent is 1. This has to give me a slope that's negative 1. And of course, I know that that's perpendicular to this isosceles 45, 45, 90 triangle, so I know that that slope is correct. If in fact I wanted to deal with concavity, if I wanted to look at the second derivative of y with respect to x twice, I'm going to need to look at the derivative of negative cotangent t divided by the derivative of x, which should be negative sine t. Now the derivative of cotangent is cosecant squared, negative cosecant squared. But because I already have a negative, this is going to give me cosecant squared t over negative sine t. And when I look at this is really 1 over sine squared, and I've got another 1 over sine, so this is really negative 1 over sine cubed t. And if I notice for this quadrant here, I am concave down. For this quadrant here, I am concave down. So I do see that confirmation for what I'm dealing with. Now, what's happening in the third and fourth quadrant? Well, this is actually something we'll address in section 10.3, because we're really dealing with this almost as if it were a polar graph rather than just a parametric graph. And we're going to be dealing with polars later on in this chapter. The last thing that I want to talk about in today's lesson is I do want to go back to the concept of arc length. When we were dealing with our arc length for a function of y in terms of x, our arc length ended up being the difference from x equals a to x equals b of the square root of 1 plus y prime squared dx. And we also talked briefly about what happens when we're looking at x as a function of y. In other words, if I'm dealing with the inverse, so the arc length ends up being from y equals some value c to y equals some value d, the integral of x prime squared plus 1 dy. But remember that both of these came from looking at the Riemann sum of the square root of delta x squared plus delta y squared. And of course, if we're looking at this as a Riemann sum, converting it to an integral, this ended up being the square root of dx squared plus dy squared. And the thing we noticed is that we didn't have our independent variable. So what we would do is we would multiply through the radical times 1 over dx squared, and the square root of dx squared gave me a positive dx to cancel out here. Same thing happened with dy. I want to use that same logic to put a dt here, which means inside the radical I have to have dt squared for each term. So for dx squared and for dy squared. And so what I'm really looking at here is my arc length is really the integral from t equals t1 to t equals t2 of the square root of dx dt squared plus dy dt squared dt. So this is my formula for arc length, and the example that we've been working with throughout here has been the function where y equals the sine of t and x equals the cosine of t, and we've been dealing with it from 0 to 2 pi. Now, we know that this graph certainly looks like a circle, but we're going to find out something rather interesting when we take this arc length. So I know that the arc length is going to be equal to the integral from 0 to 2 pi of the square root of dx dt. Well, that's negative sine t squared plus the derivative of y, which is cosine of t squared dt. So I'm looking at the integral from 0 to 2 pi of the square root of sine squared t plus cosine squared t dt. And that's a really nice identity, because that's just the integral from 0 to 2 pi of 1 dt. And so the integral of 1 dt would be t evaluated from t equals 0 to t equals 2 pi, which gives me 2 pi minus 0, or 2 pi. Now, from geometry, we had a formula for the length around the circle. We call this circumference. And the formula for the circumference was equal to 2 pi times the radius. But if we're dealing with these functions, we're dealing with a unit circle, so this is really 2 pi times the radius of 1. 2 pi. And so I notice that the circumference of a circle is exactly equal to the arc length around this parametric function. And so this gives us confirmation for these formulas that we learned back in geometry. So to recap real quick, what we're talking about here is we're talking about functions in terms of t with an independent variable of t. But we still have graphs that result from this. These graphs still have slope. These graphs still have concavity. And these graphs still have length. And what we have to do is we have to interpret the arc length, the slope, and the second derivative with respect to x for each of these graphs, because they still have a graphical meaning and a tabular meaning, as well as a functional meaning. So once again, this is Mr. Potter. Thank you for watching. Have a great day.